In this episode, we'll look at how to run multiple threads in Zephyr along with using a few thread control mechanisms like mutexes and queues. Most simple embedded applications can get away with a super loop and a few interrupts, but as your program becomes more complex, you might need to rely on multithreading. This is especially true for things like networking and user interfaces. With that in mind, let's dive in. At this point, you should have a decent grasp of kconfig and Devicetree, as we'll be making changes to the overlay files from here on out. Feel free to use the step-through debugging as needed, but I'll mostly use print statements for the simple demos going forward. Now, we'll start working on actual application demos, starting with using multiple threads in a program.
To start, we're going to make something like our original Blink demo. Let's create a new project. In there, we're going to put our boards folder. And in that boards folder, we're going to create our overlay file like we've done before. And just like we did with the Blink demo, we're going to create an aliases node and assign the myLED property to the LED0 node. In the LEDs node, we will use the compatible GPIO LED so Zephyr knows which driver to use. And we will create another node named D13 with the label LED0, and that way we will assign pin 13 to that LED pin and make sure it's active high. From there, we're going to create our CMake lists, and in that one, we're going to tell Zephyr how to build this project. We'll set the CMake minimum version, and we will tell CMake where to find the Zephyr package. We'll give our project an arbitrary name like thread demo, and we will tell CMake where to find our source files. In this case, it's just main.c. Let's save that. Don't forget to save your overlay file. You also need a prj.conf file, which we don't need to put anything in, but Zephyr does require that file to exist in your project. Then we're going to make a source folder, and we're going to add main.c to that. Let's include standard input-output so we can do things like print. We pretty much always need the Zephyr kernel, and lucky for us, that comes with the multithreading library. And we'll include our GPIO header so that we can blink that LED. We'll start off by creating our blink sleep time. This is going to be 500 milliseconds, and it will be different from our print time. So the idea is we want to have two separate threads, one blinking and one printing to the console. And let's make our print thread sleep for 700 milliseconds. Whenever you create a new thread, you will almost always want to define the stack size. This is how much memory is allotted to that thread so that you can do things like store variables. Generally, it's a good idea to statically define this memory as it allows you to create deterministic threads because you're not waiting for things like memory allocation, which might take some unknown amount of time. Zephyr highly encourages this static creation to help you create deterministic threads. And note that the main thread, our main while loop, or if you're using a super loop, that has already been defined for you on the back end. And you can adjust that in your kconfig, but it should be good enough for what we need for now. As I mentioned, it's a good idea to allocate your stack or your memory at compile time. And Zephyr gives us this macro kthread_stack_define to do exactly that. This allows the threads to be deterministic, which means we can calculate the exact execution time for the threads if memory doesn't need to be dynamically allocated or deallocated. By setting up the stack size ahead of time, it also prevents stacks from overflowing into adjacent memory areas. If you see things like weird crashes, it probably means you've had a stack overflow, and you probably need to increase this amount of stack memory available for your individual threads. If we right-click, we can go to definition, and you can see where this is defined in Zephyr, so we can keep going through that, and you can see it gets kind of deep as it goes through creating this stack for us. So let's get out of that and go back to our main code. Zephyr has these things called k-threads, and that's the actual handle to the thread itself. So you can go to the definition and you can see the information that's stored and needed for this thread. If you remember from the first episode where we had this blinking LED, we can get the spec or this struct from the Devicetree. And this macro GPIO DT spec get just gets that node information from the Devicetree, and it's using our alias myLED to do so. We're going to store it in a global variable, but feel free to put that in the initialization of the thread if you wish. I'm just mimicking what we had done in the previous episode, so it lines up and you can see how this compares to doing everything in a super loop. Next, we're going to define the entry point to our thread, this blinking thread. Notice that we give it an arbitrary function name, in this case, blink thread start. Zephyr requires that it doesn't return anything, so it needs to return void or nothing, and it must have 3 parameters or pointers to these parameters, and they're void, so they can be anything. In fact, they need to be pointers to whatever we want to pass in. So these could be integers, these could be structs, these could be whatever you wanted, but it must have 3 of them. As you will see when we go to start the thread later, you can pass in arbitrary parameters so that you can pass things into your thread. We're going to define a few variables here, specifically a return variable for when we call Zephyr functions, and the state of the LED, and that's just going to be an integer. Next, we're going to create our loop here. This will just run forever. We're going to invert the state of the pin. That's going to start as 0 and then flip between 0 and 1. Then we'll actually set the state of the LED or pin. If we run into an error with that pin setting, we will just print something to the console. It's usually not a good idea if one thread is handling your interface, like your terminal or your console, to then print from another thread. You could run into issues where things are overwriting each other. In most cases, you would do something like put a message on a queue and then have that show up in the terminal or console from the other thread. But for sake of keeping this as close to the original Blinky demo as possible, I'm just going to print K here. Then we're going to sleep this thread for, 500 milliseconds. Note that you generally want to have some sleeps in your threads because it allows other threads to run. Then we're going to define our main thread. This is our entry point for the main program. We're going to have our return value, that's an integer, and then we're going to have this KTID blink TID. This is a thread ID, and this is a particular type of struct that points to, it looks like, the actual thread. So we can go down and sure enough, it points to this thread. So remembering the KID allows us to get to that thread if we want to, say, control them, monitor them, or kill the threads from, say, like a monitor thread. As we've done before, we let the kernel initialize the GPIO on the back end. So we will just check it to make sure that it is ready prior to coming into this main function. And as we've done before, we need to set the GPIO as output, and we do that in code and not in the device tree. And what I forgot to do here is add some error messages. I'm going to do the same for this configuration. Then we're going to start the blink thread by calling this kThreadCreate function. It's going to take a number of arguments that I'll walk you through here. We need to first pass it the thread struct, which it uses to hold the thread information, but we get essentially a pointer to it in the blink thread ID. If we go to the Zephyr threads documentation, we can see thread creation, and you can read all about how threads are created, how they are suspended, run, put into waiting, or could be in the ready state, and then they can be terminated. So various interrupts and settings can put the threads into these different states. Threads can be put into the suspended state by using the kThreadSuspend function and then put into the ready state with the kThreadResume function. From there, the Zephyr scheduler puts it into the running state where the thread actually runs. Threads can also be put into the waiting state when they, for example, are waiting for a mutex or have been put to sleep. They wait for some event, like a timeout, before being put back into the ready state and run again. Right now we are starting the thread. It will go into the ready state, and the scheduler will determine the priority level to figure out when it needs to put it into the running state. If we look for kThreadCreate, we can find information about this. You can see that this function creates a thread, and here are all the arguments we're going to need to fill out. So with that KID, we can use it to get information about the thread and do things like kill it or suspend it from a monitor thread if we need to. So we've passed in that thread struct that we created all the way back here. That's a global variable for us. And then let's fill out the other arguments. So next is the stack that we initialized. And we did that outside of any running code. This was actually a global. So this is actually a global that we initialized with this macro, and it is a struct. So if we go into this definition, let's go back to where we were. This is where the macros get really confusing. So if we go back to our documentation, we can look for kThreadCreate, and it looks like this kThreadStackT, I believe this is a struct, although Zephyr's normal convention is to put struct keyword in front of it to make it clear what it is, even it's a little more verbose. If we search for this, we can find this base address of the thread stack. So if it is a struct, it's probably type deft, and it's just holding information about where the memory is. Okay, so let's go back to our code. We can close that down, come back down to where we're creating our arguments for our thread creation. So we give it the stack of where it can run or hold variables. It wants to know the stack size. Even though we've given it the base address, this thread still wants to know the stack size, which is interesting to me because why don't you just store that information in the struct? But I guess that's just an address. Anyway, with that, there's this handy macro called kthread stack size of, and we just pass it in that struct for our base address for the stack. You can also try to figure out what that is elsewhere or store it in a variable, but I find this works, so you only need to point to blink stack or the stack pointer once. Finally, we give it that entry point function, and for our purposes, this is blink thread start. So if we come up here, this is the name of that function. So you just give it the name of the function and it knows what to do with it. This is where you would pass in the 3 different arguments. I'm gonna pass in nothing, so null right now. These could be integers, these could be structs, but note that you have to pass in a pointer, so it would be the address of that, and then you would get that actual value later in the function if you dereference the pointers because these are coming in as pointers. So you would just be able to get, say, arg1, and that would be the value of something. Next, we set the priority, and it is similar to Linux priority levels in that lower numbers mean higher priority. So let's take a moment and look at that. So if we go to our information here, we can go to threads. We can look for thread priorities, and I saw that in the table of contents here. Notice that it says numerically lower priorities take precedence over numerically higher. So for example, if we have thread A of priority 4, thread A is going to have a higher priority over thread B if thread B is set to priority 7. So it's like Linux, but might be different or opposite of what you might be used to in other RTOSes. What's interesting is that there are negative numbers for priorities, and negative numbers will always have higher priority than positive integers. You only use negative priorities when you want to use a cooperative thread. This is a thread that must explicitly give up control. This is similar to maybe the async IO Python library if you've played around with that. Positive numbers are preemptible threads. This means that the scheduler can look at the priority numbers and determine that a higher priority thread can preempt another thread. So keep that in mind as you're writing this. You can specifically create cooperative threads, which is useful if you want to have something that preempts all your other threads, but then make sure you specifically have it give up control. That is going to be very important, otherwise you will just end up in a loop forever because cooperative threads will run forever, they will hog the processor unless you explicitly have them give up control. This is just something interesting to note about Zephyr, that you have the possibility of doing both cooperative and preemptive threads. Let's scroll down a little bit and you can see a nice little diagram here talking about the different priority levels. So even including priority 0, these are all the preemptible threads on the positive side, and on the negative numbers, these are all the cooperative threads. A general rule among developers is that 0 to 10 is considered high priority, 11 through 49 is medium priority, and 50 through 127, which is the maximum number available for your thread priority, those are going to be your low priority threads. So that's the general grouping that you will see among developers. It's not enforced, it's just kind of a levels to remember. All right, let's go back to our code. Now that we've set our priority, and after that, this is where we set our options. And if we go back to the documentation, we will want to look for the thread options in the table of contents. These are the possible options you can pass to this particular parameter. Note that these work like flags, so you could do kessential or ksse regs, and this would pass in both of those options. I recommend making a note of this kessential option. This tells the kernel to treat the ending of the thread as a fatal system error. So if something happens and your thread exits, it pretty much crashes the whole system and spits out error logs. So this marks the thread that you're creating as essential. The whole system just crashes if something happens to this thread. There's also this fp regs. This tells the kernel to save and restore the contents of the floating point registers when scheduling the thread. This can help if your particular thread is working with floating point numbers, if you're doing a lot of math. The others have some uses, but those are the two big ones I recommend paying attention to, as you might likely need those in the future if you're creating some complex system. All right, back to our code. And the final argument here is k no wait. The parameter here is the delay. This tells the kernel how long to wait before creating this thread. You can define a k timeout struct here, which can be, say, a number of milliseconds or seconds. And we're just going to use k no wait, which just means start the thread right away. And just like we've done before, we're going to have our super loop in this main thread. It's just going to print hello to the screen and then sleep. And then in our case, it's going to sleep for 700 milliseconds. It is a little different than the blink timer. It's to show how we can have these two threads running with different timings. And like any good main, we're going to return 0, even if we never get there. Note that this main thread, by default, runs with a priority 0. So it's the highest possible priority that is preemptible. You can change this in either code or using kconfig, but for now we'll just go with the basics, knowing that this thread, this main thread, can preempt our blink thread. Because the executions of these threads are so short, they probably won't ever collide. With that in mind, let's bring up a terminal. And we're going to do this in the workspace. We're going to always reconstruct that build folder, set the board to our ESP32S3 DevKit C, specifically the ESP32S3 SoC and the Pro CPU processor, and we're going to pass in our overlay file. Let's go ahead and build that. And it does not like this. And it looks like, oh, I put everything in the boards directory. Oops, let's move these out. Yes. CMake list should be out here, move, PRJ should be out here, move. There we go. It should just be boards, overlay file, SRC, and then CMake list and PRJ. Let's try that build again. Let's Control C. It doesn't like, man, I am misspelling stuff today or putting things in the wrong places. Let's go to CMake lists. Let's correct this spelling error. Save that. Don't forget to save our main.c. Let's try this build one more time. And we will wait while that completes. All right, with that done, let's bring up the terminal on our host computer. Make that a little bigger so you can see what's going on. I'm in the Introduction to Zephyr folder. Don't forget to activate the virtual environment for Python. And as we've done for pretty much every episode, we're going to call the ESP tool from Python, give it the COM port for our board, and we're going to tell it where to flash, and we're going to point it to the 08 demo multi-threading folder in there, build, Zephyr, and zephyr.bin. Wait a moment while that flashes. And we will connect to it with a serial terminal. And you should see hello flashing to the screen from one of the threads.
And the LED should be flashing at a different rate from the other thread. It's not an impressive demo, but you know that the LED is being controlled by its own thread. Mutexes and semaphores are used to prevent threads from accessing the same resources at the same time and to help synchronize thread execution. I won't dive too much into the theory behind these synchronization techniques, but I recommend checking out my Introduction to RTOS series if you'd like to learn more.
So with that done, let's do Control, close bracket to exit out of that terminal and come back to our code. I'm going to close out of this terminal so we can see what's going on. And let's talk about synchronization techniques. Specifically, I'm going to demonstrate mutexes, and semaphores are quite similar. I recommend checking out my RTOS series if you want to learn more about the various concepts behind real-time operating systems and multi-threading. We won't dive into that a lot here, but I will give you a brief demo just to get you started on how this works in Zephyr. So what I'm going to do is delete this build folder, and I'm going to make a copy of this multi-threading demo so we can start off with the same thing. I'm going to basically modify it so we don't have to rewrite everything. And let's rename this to demo mutex. Let's close out of the files here. And in mutex, the boards should be the same. We have to make a quick adjustment to prj.conf. And we're going to add the console subsys and console getLine arguments. These symbols turn on the subsystem that allows us to interact with the console rather than just printing to the screen. It enables the libraries that capture keystrokes, and we can do things like get an entire line when somebody enters that. Unlike, say, Arduino, where that's built in and it comes by default, this is a specific subsystem you have to enable. And I figured this out by tinkering around with kconfig and menu config and looking at the documentation, but these are the lines you need to add in order to do things like get line from the console. So let's save that and let's open up our source code. In here, we're going to include console subsystem, which is console.h. The idea behind this is that there are two threads. One is going to run the console, the other is going to run the LED. The user is going to be able to enter plus or minus into the console to increase or decrease the speed of the LED, or rather the sleep period. And to do that, we're going to have our sleep period be a global variable that's protected by a mutex. So we're going to adjust our sleep settings here to prevent the user from going into negative values or sleeping way too long that they basically just sleep the processor forever. We're going to specify the minimum and maximum values that the blink thread can sleep for. In my experience, 256 bytes is the bare minimum to run a thread in Zephyr. It was barely enough to blink that LED, so usually you want to increase this. 512 is a small size. Most threads you will see in a lot of applications are like 1024, starting there. We'll do the same thing with the input thread. We are going to need to store a small buffer of characters that we read from the line. Unlike the previous example where we had a thread run separately from the main thread that was already defined, we're going to run two separate threads and then basically sleep the main thread. To do that, it means we need to define the stack areas for both threads, the blink stack as well as the input stack for the input thread. As with the blink thread, we need to create our own user interface or input thread, and that's going to be a handle to that. To make life easier, we're going to define the mutex as essentially a global variable. That way both threads can access it easily. And we will create our shared resource. Once again, this is another global, or rather static, so that it's only seen in this file. This is the value of the actual sleep rate for the blinking thread. This is shared because the input value can adjust this, and the blink thread needs to be able to read this to know how long to sleep for. We'll keep the LED struct as another global here, or unique to this file. Then we will define our separate input thread. We're going to have a variable that remembers how much to increase or decrease the sleep value by, and we'll say starting this thread just so you can see where it starts. We're going to use this console getLine function that is available from Zephyr. This will look for a new line character input into the console and then return everything up to that point. Note that this is a blocking function, so be very careful with this in threads, or make sure that the thread has an appropriate priority such that it doesn't block other threads. And that's why I put the note that this particular function is blocking. Next, we're just going to get that line and see if the first character is a plus or minus. This is not a particularly robust interface. It's just saying, hey, is that first character plus or minus? If so, set this variable, and we're going to use that to control the blink rate rather than trying to read a number or anything like that. It's just going to be a very simple interface, and this is a very simple way to read this first character. If that first character is not plus or minus, just skip back to the beginning of the loop and wait for a new line. This is where the magic happens with the mutex and the shared resource. We're going to increase or decrease the wait time, bound that value, make sure it doesn't go outside of the min or max. And we're going to lock and unlock the mutex so the other thread can't access the shared variable during this time. To lock the mutex, we're going to use kmutexLock. This is a Zephyr function. We pass it in the address of the mutex, and we pass it in how long we're willing to wait for that mutex. In this case, we say wait forever. This puts the thread into the waiting state while it waits for the mutex to be ready. Once the mutex is ready, the scheduler checks to see the priority of this thread. If it's the highest priority thread, it goes ahead and runs this line to grab the mutex and then run the next lines. And just to be lazy, we're going to increase or decrease the blink sleep amount by some increment of 100. Note that we cast that increment value from an int 8 to an int 32. I suppose I could have just made that variable int 32, but whatever. And then we clamp that value between the minimum and maximum values. So if it tries to go over 2000, it stops at 2000, or if it tries to go under 0, basically if it goes negative, it'll just clamp it to 0. Finally, we protect that resource by unlocking the mutex. This allows the other thread to read the shared variable, knowing that it's not going to change in the middle of that read cycle. Then, just for fun, we're going to print the new sleep time to the console. The blink thread is going to be a little bit different. We're going to keep that return value and the state value, but we are going to add this sleep ms because we're just going to have the thread remember that sleep time and let the global variable update from the console. We're going to say that the blink thread is starting. Once again, not a great way to do this. You generally want to put a message on a queue and have the console thread handle that. But just for the sake of simplicity, we'll put it here so we don't have to create a queue. If you want to challenge yourself, try creating a queue system that's like an input queue and an output queue, and have the terminal thread or the console thread handle those messages for you rather than printing directly from other threads. Just like we did in the previous thread, this thread is going to wait for that mutex to be unlocked. We will wait forever if necessary. This will put the thread into that waiting state. And we will read that global variable, that shared resource of the blink sleep ms, and store it into our sleep ms local variable, and then immediately unlock the mutex so that the other thread can go ahead and write to it. The actual pin toggling will remain the same. It's just toggling the pin back and forth. And instead of this global variable for this sleep here, we're going to change this to this local variable because it is potentially updated every cycle. Now let's scroll down to our main thread here. In addition to that blink TID, we're going to add an input TID because I like things to be neat. We're considering the input thread to come first, so we'll put it there. We'll make sure that the GPIO is initialized and set as output. And we have to call this magical getLine and init function. This initializes the console to allow for input to that console. This allows us to call that getLine function. Let's close that, return to here. Then we're going to initialize the input thread. And it's going to look a lot like our blink thread. So we're going to add all of our arguments here. We will add the input thread struct that we created, the stack that we defined up in the beginning, the entry point function, which is input thread start, and we're going to pass in nothing for the 3 arguments or 3 parameters. I'm also going to set this as a lower priority. Remember, higher numbers are lower priority. So I'm going to set this to priority 8. So the blinking LED takes priority over the console. We're going to pass in no options. And as we did before, we are going to tell the thread to start immediately by passing in k no wait. Now we're not going to print anything to the console. The blink thread will be the same. Both of those threads will fire off. And we will do nothing in our main loop here. In that main thread, we will fire off 2 new threads. And this main thread is just going to sleep. You could actually delete this main thread if you know you are no longer going to use it. But just for the sake of simplicity, we'll fire off the 2 threads and then just put this main thread to sleep forever. Let's save that function. Let's bring up our terminal. And we will actually remove this terminal. Let's go back to this terminal. We will go out to 08. We're going to do the demo mutex. And we're just going to call the same. Oops, I need to go 08 demo mutex. That's what I actually want to do. CD into that. And then we will call the same function to build, but we are now in that mutex demo. We will let that build. With some luck, that should build, and we can open up our console here. Let's flash it, but remember we need to go into this 08 demo. Nope, we want to go into the demo mutex and build zephyr.bin. Let's flash that. And let's open up a serial terminal. You can see that the 2 threads have started. Let's try entering plus. You can see that it updates the sleep to 600. And we can keep increasing that. And you can see how the LED takes longer and longer to flash. We can also enter minus down to the point where it's basically just steady. However, you can see a problem when I try to enter additional pluses here, even though that is steady. Can you figure out what's going on? If you guessed priority levels of the threads, you would be absolutely correct. So let's come down here. You'll notice that my input thread is a lower priority than the blink thread. And because the delay is 0, it means that the blink thread no longer waits. It's just cycling the LED as fast as it can, and because it's higher priority, it never gives up control to this console thread. So what we need to do is let's try making the input thread, this terminal one, a higher priority, and we will make this one a lower priority. So let's save that. Note that by default, if 2 threads have the same priority, Zephyr's scheduling algorithm, by default, chooses which of the threads have been waiting the longest to run next. So with that saved, let's go ahead and rebuild. With that done, let's try to reflash. So we will control close bracket. Let's reflash it, and let's open up our console. All right, both threads are started. Let's bring this down to 0. And sure enough, we can now increase it again. So back down to 0, the LED should be steady. And we can increase the timing by entering plus into the console. For your challenge, I want you to use your MCP 9808 driver that you created in the device driver challenge or the official JDEC JC42 driver. Your job is to create 2 separate threads. One of the threads reads from the sensor, it gets that temperature data and writes that data to a message queue. The other thread waits for data on the queue and then prints out the value. Note that I'm not printing out the value as soon as I get it. What I want you to do is let the queue fill up, say 5 to 10 values or for some amount of time before printing out the temperature readings in a burst. So you see here that the messages are getting put on the queue whenever the sensor is read, once every, say, half a second, and then every couple of seconds, all those values are printed out. So you get this burst read. This is particularly useful to both demonstrate how queues work, as well as demonstrating how you might do something like queue up messages for a Wi-Fi, say once a day when you want to save on energy. If you need some help, I highly recommend going to the Zephyr documentation and looking up message queues. This API is particularly useful. It works in a similar manner as mutexes and semaphores. Feel free to use mutexes and semaphores, but you should definitely use a message queue to store a bunch of temperature reading values at once so that your terminal thread or your console thread can read all of those and print them out in a burst. Just like with message queue, you can find information on semaphores, which we didn't get into, but feel free to check out that RTOS series if you'd like to know more about the theory behind semaphores and how they're used and different from, say, mutexes. And here's the documentation on mutexes. Zephyr has great documentation on these, so check them out and good luck with this challenge.
I hope this helps you get started running multiple threads in Zephyr. Don't forget to check out my Intro to RTOS series if you'd like more theory on multithreading. Next time, we'll see how to use interrupts to respond to pin changes and timer events. See you then.